All right, I got a question, a momentum question from the hard book here. Not a surprise. It talks about this projectile here that gets launched up, and when it gets to its highest point, and one of the things that hopefully is going on in your mind right now is that, okay, at its highest point, it only has a velocity in the x direction. All right, keep that in mind, because then it's going to explode into three pieces. And if I read this right here, let's see. It says a projectile has a mass of 2 kilograms. It is fired into the air at an angle of 40 degrees to the horizontal with a speed of 50 meters per second. At its highest point in flight, the projectile breaks up into 3 parts: a 1 kilogram mass, a 0.7 kilogram mass, and a 0.3 kilogram mass. The 1 kilogram part falls straight down, so this will be the 1 kilogram. The 0.7. So the 1.0 kilogram part falls straight down after breaking up with an initial speed of 10 meters per second. The 0.7 kilogram part moves in the original direction. Okay, so 0.7 kilograms, moving in the original direction. And the 0.3 part goes straight up. So 0.3 kilogram goes straight up. Okay, question A. Find the speeds of the 0.3 and the 0.7 piece immediately after breakup. So this is where I'm going to apply conservation of momentum, since this explosion is internal. There are no external pieces, and that was our argument about when the principle, that would be initial, when our principle of conservation energy would work. So initial and final are equal in the x direction, and initial and final are equal in the y direction. All right. Why don't I start with the x direction? So immediately before the collision, I would have a 2 kilogram object moving with and here is going to have a chance to go back a few chapters. At this point where it explodes, at its highest point, its velocity in the vertical direction would be 0. And its horizontal would be unchanged. Remember, the acceleration in the horizontal direction is 0. So if I come back over here to the beginning, it would be 50 meters per second times the cosine of 40 degrees. So that is the momentum of this projectile right before it explodes. Again, this is the horizontal speed, the x component, and this is the mass. Now, in the vertical direction, it has 0 momentum. So I'm going to look at the initial momentums. And again, what I mean by initial is right before the explosion. I don't want to say all the way back in the beginning here, because remember, momentum is only conserved if you include the 2 interacting or 3 interacting or 4 interacting objects. And while it's going up, the interaction is between this launching object, this projectile, and the Earth. And so to apply conservation of momentum from all the way back here at the beginning means I need to include that force from the Earth, or I need to include the object of the Earth. And I can't and I don't. And that's kind of a big crutch of this problem. When can you and when you can you not apply conservation of momentum? And so what I was saying is you can apply it if you include all the interacting objects. And so the part that has to do with gravity, we're not including the Earth. So we don't want to include the motion with the Earth. But immediately before and immediately after the explosion, all of those are from the whatever making it explode. I'll just say there's gunpowder inside making it explode, kaboom. That is when one pushes off the other, they're equal and opposite. That's when momentum is conserved. So I can say that right before the collision and right after the collision, because it really hasn't moved with the effect of gravity, momentum is conserved. So I just want to make that really clear when I'm applying momentum conservation and when I am not. So this is immediately before the collision. I know I say initial, but I mean initial as right before the collision, not initial as when it was launched, okay? And that's why I'm going to put here 0 momentum in the vertical, because right before the explosion, it's at its highest point. It's not moving up or down in the vertical direction. Its velocity in the vertical direction is 0. All right. Maybe we're saying one more time and I better move on. But to apply conservation of momentum, we have to make sure there's no outside influences, or what we have to say is that 2 objects interacting or 3 objects interacting have to be considered as part of the project. So the Earth is not, but the 3 pieces and the gunpowder is. So immediately before and immediately after the explosion, I could apply conservation of momentum, but not on the way up and not on the way down, because the interaction is with the Earth, and I'm not including that as one of my objects. All right, so here we have it. We have the initial momentum, and again, this is at the top, right before the explosion, and the initial momentum in the vertical direction. So X direction, Y direction. Now, they have to equal after. All right. Now, they made it kind of easy for us in the sense that these 2 go in a vertical direction. So the only thing having momentum is this 0.7. And so then I can say, what is its speed in the X direction? And I'll do that math in just a second. When I come over to here then, again, they made it easy. This is all vertical. So this would be 0.3 times the velocity of, and just to make it stand out, I'll say y. So that's the one going up. And this one's going down, so it's minus 1 kilogram times its speed of 10. And so again, we can solve for that speed. Okay, so grabbing my calculator here, the horizontal piece would be, let's see, 2 times 50 times cosine of 40. I better check that I'm in degrees. Okay, I am. And so that is the momentum before the explosion in the X direction, and it has to remain that. So if we divide by 0.7, that 0.7 piece must be moving now with 109.4 meters per second. By the way, if it helps, in order for these pieces to go straight up relative to the moving object, they'd kind of have to be pushed kind of in a backwards angle like that. And it's that push backwards that then results in a net, because of their forward and then push back, is that they go straight up. But it also, that kind of back at an angle is what thrusts this one forward at such a large speed. Same thing here with this one going down. In order for the net result just to be down relative to this exploding projectile, it's got to shoot it off towards the back because it's already moving horizontally at whatever this speed comes out to be, 50 times cosine of 40. So it kind of shoots it off that way, which is why the net result is that it just goes down, but it's also why this one gets forward. And so these 2 get angled back, pushing this one forward. So this one's got to make up for all that momentum. It's a small object, less than half of what it is, so it's got to be going really fast. Okay. Now, over here, same idea, is that in the vertical direction, it looks like we've got the heavier one going down at 10. So the lighter one, and quite a bit lighter, it's only 30% of the heavier one, this has to be going up quite a bit. Looks like 30, about, looks like it's going to come out to be about 33 in order for these numbers to match out here. Let's see what I get here. This would be a 10 moved to the other side, divided by 0.3, and so 33.3 meters per second is how fast that one has to go up. So again, this one being lighter has to go up really fast to match this heavier one going down in order that they have the same momentum. All right, so I guess I've answered, this right here would be A, where it says find the speeds of the 3, here it is, and the 0.7 pieces immediately after the breakup. Okay, part B on this says how high from the breakup does the 0.3 kilogram piece go before coming to rest? Now, there's a couple ways we can do this. One is to just go back to our old kinematics, because we know that once it breaks apart, we can just think of it as an object pushed straight up. And this takes us way back to chapter 2. And the equation without time is what we call the third kinematics equation. So that's what came to my mind first. But also conservation of energy from the last chapter would be nice also. And so whichever approach you want to use, he doesn't say how to do this. So I'll just go all the way back to chapter 2 and say, all right, the final speed is going to be 0, meaning it starts with some initial speed, which is this 33.3 going upward, and then it has an acceleration of negative 9.8, and then I'll just call this the delta x. Actually, it might be better to call it a delta y since it's going up in a vertical direction. But when we derived this, we said this was just one-dimensional motion, and we emphasized x did not mean just horizontal. So call it delta x or delta y. That much doesn't matter, but whatever you want to call it, and I'll kind of stick to my delta x, we're going to figure out how high this goes. So I'm going to take that number and square it, move it over to here. The negatives cancel, and then divide it by a 2, and also divide it by a 9.8, and we're looking at about a 56.7 meters is how high vertically that's going to go from this spot here. Now let me be careful here. Did they say from this spot or from the ground? Because it already went up before it exploded. B says, how high from the breakup point does it go? All right, so this is as far as I have to go. I don't have to figure out how high it got to actually get this. It says from the breakup point. Okay, and then C, where does the 0.7 piece land relative to where it was fired from? Now that one, I've got to then break this into, well, how far did it originally go before the breakup, and then how far does it go after the breakup? All right, and I guess I'll just do that in order. Why don't we just figure out how far horizontally does it go before the breakup? And so I'm going to do a projectile motion calculation here. And I'll tell you what, I'll start with the y direction and say y final, or velocity final in the y direction, is equal to initial in the y direction plus a t. This can be helpful because I know at its highest point, its vertical velocity is 0, and it starts off with a speed of 50 times the sine of 40 degrees. The acceleration is 9.8, and so the unknown in the y direction would be a time, and this will then tell me how much time it took to go up to that highest point, where I can then use it to figure out how far horizontally it goes. All right, so let me go ahead and put in the 50 times the sine of 40. All right, so it looks like 32 is its original vertical speed. So if I then divide that by 9.8, I get a time of about 3.28 seconds. 3.28 seconds. So I'm going to use that when I put it into the horizontal motion, which says x equals x initial times initial velocity in the x times time plus 1/2 axt squared. So that's our kinematic equation number 2, gives us distance. So I used kinematic equation number 3 in the y direction to figure out time, and I'm going to use it over here. And I'll just kind of remind you then that I guess I'm looking for how far did it go, so x minus x naught. And the horizontal acceleration is 0, so I can just get rid of that term. So this is going to be the 50 times the cosine of 40 degrees, and then multiplying it by that 3.28 seconds. So this might be the easier half of part C, just how far did it go before the explosion. Okay, so 50 times cosine of 40 times 3.28, coming up to 125.6 meters is how far it goes before it actually explodes. Okay, now once it explodes, we have a whole new speed and direction. So I'm going to just kind of draw a little picture here of something going horizontal, and it's going to do something like that. But I'm going to kind of do the same logic here and do an x and a y. And again, how far horizontally would it go? X minus x naught equals v naught t plus 0. And let me just say I'm really doing the same second kinematic equation where I'm saying how far did it go? And of course now we have a different horizontal speed. And that's what we got out of A. In A, we got the horizontal speed as 109.4 meters per second. But just like we did the first half of C, I can use the vertical to get the time and then come back and use it. So I'm going to write this out, but I can't really go anywhere with it because I'm kind of stuck with how much time. And that would be then the falling of this. How far did it fall? Now, fortunately, going back to our projectile motion, we argued that if something is in a projectile, regardless of what its horizontal speed is, we treat the vertical separate of that. Here's why that's important. Let's just say it did not explode. See, if it did not explode, it would have taken the 3.28 seconds to get to the top, and that's what we used. Of course, then we said it'd explode. But if it hadn't exploded, it would be as if you just dropped something and it had a 0 vertical speed and fell straight down. So even at the piece that explodes, as long as that piece has a horizontal speed of something different, that's irrelevant. The only thing that would shorten or change the time to go down is if the vertical speed had changed, and it didn't. This one said it was purely horizontal. And so my point is the fact that this little piece now has a much bigger horizontal speed than before the explosion. So again, this is the speed after the explosion. Before the explosion, it was, well, these two together, which was like 32. But I'm going to just say it again, projectile motion, that doesn't matter. The x and y are independent of each other. So when it explodes, something with 0 vertical speed is going to take the same amount of time. And that's the same as if it didn't explode. And so my point is, right here would be the time to go down. It's equal time up and equal time down. This is the time it would take to go down if it didn't explode. It's also going to be the time to take down now that it did explode, because it doesn't have any kind of, after the explosion, any kind of upward motion or downward motion. Okay, so this would be a much greater speed, but the time is still the same time it took to get up, and so it would be the same time to go down. So 109.4 times 3.28 means it's going to go 359 meters during this dropping down effect. So let me just come back and read this. C says, where does it land relative to where it is fired? So I think I need to add the 120, I'll just call it 6, together with the 359 to get the total. So 15 carry 1, 7, 8, and 4. So 485 meters would be the total distance it travels in the horizontal. So a lot of projectile motion going back. Really, the only thing for this chapter is this two-dimensional conservation of momentum. And then the rest is throwback to projectile motion stuff. All right. Hope that all helped. Take care.